In this first example, we are going to answer some questions about parallel plate capacitor that is connected to a battery. We are told the surface area of the plates is 2 square centimeters and the distance between the plates is 1 millimeter. Therefore, because we are working with a parallel plate capacitor, we could say the capacitance of this capacitor will be given by epsilon naught A over D. Now, before I go ahead and plug numbers in, remember that we need to be working in our base SI units. So I need to convert the area and the distance to square meters and meters respectively. The distance between the plates of 1 millimeter will be 0.001 meter, but there is a subtlety in converting the area. The area is given as 2 square centimeters. But because I have two instances of my unit centimeters, I need to cancel both of these instances. So I would multiply the area by 1 meter over 100 centimeters and multiply it again by 1 meter over 100 centimeters. And now both of these centimeters in the denominator will cancel with the centimeters squared here. So I find the surface area of the capacitor plates is 2 times 10 to the negative 4 square meters. Another way we could think about this conversion is imagine a square that is 1 meter on a side. If this square is 1 meter on a side, then I could also equivalently say that this square is 100 centimeters on a side. Therefore, I could say 1 square meter is equal to 10 to the 4 square centimeters. Now we are ready to plug numbers in to determine the capacitance of this capacitor. I could say the capacitance is given by 8.85 times 10 to the negative 12 times the surface area of the capacitor in square meters, which is 2 times 10 to the negative 4, divided by the distance between the plates. We're told the distance is 1 millimeter, which is 0.001 meters. And when I plug these numbers in a calculator, I find the capacitance of this capacitor is 1.77 times 10 to the negative 12 farad. And if I choose that I want to include an SI prefix, I could also say this is 1.77 picofarad. We will now calculate the charge that accumulates on the capacitor plates when it is connected to a 4-volt battery. Because there is an increase in electric potential when we move from the negative to the positive terminal of the battery of 4 volts, there must be a corresponding drop in electric potential of 4 volts as we move from the side of the capacitor that's connected to the positive terminal to the side of the capacitor that's connected to the negative terminal of the battery. To find the charge that accumulates on the plates, we will use Q equals CV. The capacitance of the capacitor that I'm plugging into this equation is the 1.77 times 10 to the negative 12 number. Farad is the base SI unit of capacitance, so I could say the charge that accumulates on the capacitor plates will be 1.77 times 10 to the negative 12, and there is a drop of 4 volts across the capacitor. So I multiply that by 4 for my V, and when I put these numbers in the calculator, I find that the charge that accumulates on the capacitor is 7.08 times 10 to the negative 12 coulombs of charge. To determine the energy stored by the capacitor, we have two options. We could either say the energy stored by the capacitor is given as Q squared over 2C, or we could say the energy stored by the capacitor is 1/2 CV squared. I will choose to go with the latter. Both of these options will give me the correct result, but I don't want to put a number with an exponent in a denominator. I feel the math of this second equation is often simpler, so that's why I'm going to go with it. So I could say the energy stored by the capacitor is going to be 1/2 times the capacitance of 1.77 times 10 to the negative 12 times the voltage drop across the capacitor squared, which is 4 volts squared. When I plug these numbers in a calculator, I find that the energy stored by the capacitor is 1.4 times 10 to the negative 11 joules of energy. We will now demonstrate 3 different methods for determining the strength of the electric field between the plates of this capacitor. On an exam, if you were asked to find the strength of the electric field, you would only need to demonstrate one method correctly. However, for the purpose of an example problem in lecture, I wanted to show 3 different methods for answering the same question. The easiest method for finding the strength of the electric field would be to recognize that between the plates of a parallel plate capacitor, the electric field is going to be uniform. Because of this, I could write that the voltage drop between the plates of the capacitor will be given as E times D. Normally, we would have a negative sign in this equation, but I did say voltage drop, implying that there is a negative sign there. Also, we only care about the strength or the absolute value of the electric field, so I'm not really going to worry about the negative sign. We are told the voltage drop across the capacitor is 4 volts, and the distance between the capacitor plates is 1 millimeter, or 10 to the negative 3 meters. Therefore, the strength of the electric field between the plates of this capacitor is 4,000 volts per meter. Another way we could calculate the strength of the electric field between the plates of a charged capacitor comes from energy density. We learned that the energy density between the plates of the capacitor is given by 1/2 times epsilon naught times the strength of the electric field squared. Let's take a moment and think about what is energy density. Energy density is the number of joules per cubic meter in a given region of space. The energy that is stored by the capacitor is stored in the electric field, and the electric field exists between the capacitor plates. So that energy is going to be distributed in the volume between the plates of this capacitor. So I could say the energy density will be the energy stored by the capacitor divided by the volume between the capacitor plates. And then I could set that equal to 1/2 epsilon naught E squared. The energy stored by the capacitor we found was 1.4 times 10 to the negative 11 joules. And the volume between the plates will be the area of the plates times the distance between the plates. That would essentially be length times width for the area times height, being D. Plugging numbers in, we find that the energy stored by the capacitor is 1.4 times 10 to the negative 11 joules divided by the volume of the space between the capacitor plates, which is A times D. So I have 2 times 10 to the negative 4 times 10 to the negative 3. And then I set that equal to 1/2 times epsilon naught, 8.85 times 10 to the negative 12, times the strength of the electric field between the plates squared. I then could go ahead and solve for the strength of the electric field, and I find E is equal to 3977 volts per meter, which is basically the same result we found previously. The slight difference is just due to rounding. The final method we will demonstrate for determining the strength of the electric field between the plates of this capacitor will have us imagine that the plates of the capacitor resemble an infinitely large sheet of charge if we are standing between the plates. We have said that the strength of the electric field due to a single infinitely large sheet of charge could be written as sigma over 2 epsilon naught. Sigma is the surface charge density. How many coulombs of charge are spread out per square meter on your infinitely large sheet of charge? We are assuming that the plates of the capacitor resemble an infinitely large sheet of charge. We have some amount of charge spread out over some amount of area. So for this problem, I could say sigma is equal to Q over A. Because we have 2 plates, we will have 2 contributions to the electric field. So the total electric field between the plates of the capacitor will be double this. Therefore, I could say the strength of the electric field between the plates of the capacitor will be equal to 2 times sigma over 2 epsilon naught. Sigma is Q over A, so I'll have a Q over A over 2 epsilon naught. I then could cancel out the 2's and say the strength of the electric field between the plates of the capacitor could be written as 7.08 times 10 to the negative 12 divided by 2 times 10 to the negative 4 times epsilon naught, 8.85 times 10 to the negative 12. And when I put these numbers in a calculator, I again find that the strength of the electric field between the plates of the capacitor is going to be 4,000 volts per meter. We will now consider a problem involving a spherical capacitor. A spherical capacitor consists of an inner sphere of radius A, and that sphere is surrounded by a spherical shell of radius B. We want to somehow connect the inner sphere to some of the elements in our circuit, so in order to accomplish that, we will need to drill a very small hole in the outer shell, and that allows us to run a wire between the inner sphere and the other circuit elements. Even though the picture as drawn is not a perfect spherical capacitor, it is a close enough approximation that we could treat it as such. In this particular problem, we're told that the inner sphere has a radius of 5 millimeters and the outer sphere has a radius of 5.5 millimeters. So the first thing we're going to do is we will calculate the capacitance of this capacitor. We cannot use C equals epsilon naught A over D because that equation applies exclusively to parallel plate capacitors, which this is not an example of. So we could go to the textbook or the PowerPoint slides, and we see that the capacitance of a spherical capacitor is given as C equals 4 pi epsilon naught A times B over B minus A. When I plug numbers into this equation, the two radii, A and B, need to be written in meters. We are given A and B in millimeters, so we do need to convert these values. So I would say the capacitance of this capacitor is given as 4 pi times epsilon naught, which is 8.85 times 10 to the negative 12. And then I have A times B, so I'll have 0.0050 times 0.0055 divided by B minus A, 0.0055 minus 0.0050. When I send these numbers through a calculator, I find that the capacitance of this capacitor is 6.12 times 10 to the negative 12 farad. At this point in the problem, every step moving forward is going to be identical to the previous examples we have considered. Even though we are working with a different type of capacitor, I now know the capacitance. So if I wanted to know the amount of charge that accumulates on the spheres, I would use Q equals CV and plug in the value for C we just found. If I want to know the amount of energy stored by the capacitor, I would use 1/2 CV squared or Q squared over 2C. This particular example asks us to find the energy stored. So I would say the energy stored by the capacitor will be given as 1/2 CV squared. Because the spheres are connected to either end of a 12-volt battery, that means there will be a potential difference of 12 volts between the spheres. So I could then say the energy stored by the capacitor is 1/2 times 6.12 times 10 to the negative 12 times 12 volts squared. And when I put these numbers through a calculator, I find the energy stored by the capacitor is going to be 4.4 times 10 to the negative 10 joules.